The title of today's lecture is File and Directories. Let me first explain the concept of file. File is a linear array of bytes. Linear array of bytes. These are our bytes. That's the definition of the file in the Unix. That's very important. In some system, a file is a set of records or database records or key value pair. So there are a variety of ways of defining files in a file system. In Unix operating system, it takes the very simple definition on the file. File is an array of bytes. And each file has low-level name as inode number. So internally, each file has a number. That's the name of the file. But for us as a user, nobody sees a file as a number. We see a file as a string, like hello.c or something like that. So I'll come to that point later. So that's the concept of file. File is an array of bytes, a linear array of bytes. That's a very important concept. And the second thing is the concept of directory. Directory is a file. It's also a file. It's a special file. And it consists of a list of file name and low file name pair. So low level file name pair is inode number I just mentioned in the above. So directory is a set of file. It contains a pair. Blah blah blah. So using the concept of a directory, we can organize a set of files into the hierarchical structure. For example, there is root directory, and there are two subdirectories, foo and bar. And under the foo, there are bar.txt. And under another directory bar, there are two subdirectory, bar and foo. And under the foo, there are bar.txt file. So there are two valid files, two data files, bar.txt, under the root, under the foo, under the bar, this one. And then second directory, root /bar/foo/bar.directory. And there are five valid directories. There are two valid files and five valid directories. Okay. So I'm going to explain the basics of the file interface. Interface means a set of functions that manipulates a file. The first function is creating a function to create a file. And how can you create a file? We're going to use the Open System core with o_create flag. So we create the file under the name foo, and we use o_create, and that's going to be write only. And then the initial size is set to 0. Okay, this is user permission. And then the Open System core returns a file descriptor. File descriptor is an integer. It is used to access the file. So we can use the read file descriptor. We're going to come to this point later. Each process has an array of integer that is called file descriptor table. File descriptor table. And a file descriptor is an index in this table. So this is 0, 1, 2, 3, 4, and such and so forth. And first, this is array pointers actually. This is point to some data, some object. And this, each entry in the file descriptor table points to the file object. And file object contains a variable called offset. And also file object contains a point to the inode. It is very difficult to make a presentation in complete order. You're going to come to the point about what file object is and what the inode is later in the lecture, but not now. So I can only have to tell you that there is file descriptor table, and each file descriptor table has a pointer to the object called file object, and most important data structure for file object is offset within a file. Offset is the position within a file where the read and write system calls are applied. So this is struct file. This corresponds to this object, file object. And then this is the array of pointer. And each operating system defines maximum number of file descriptors in the file descriptor table. It is corner global variable, and it changes, but in most recent Linux, the size of the file descriptor table is 256. Next interface is reading and writing the files. Let's consider the command cat. So before looking at the details of the command cat, we are going to create a file foo, which contains the string hello. So we type command echo and then hello, and then redirect it to the file foo. And then file foo will be created, and it contains a string hello. So using the command strace, we can follow the system call trace in the course of executing the command cat. Let's trace cat foo, and then there is r, and then we perform a foo, and then as a result of opening a file foo, it creates a file. It returns a file descriptor number 3. You have to look at the details of how and why the file descriptor number 3 is returned as a result of opening a file foo. File descriptor table is a list. It's an array of pointers that points to the file object, and then the first, second, and the third, the index 0 and 1, 2, is dedicated for stand.input and stand.output, and third one is stand.error. So if a process opens a file for the first time after the process is created, it returns a file descriptor 3 because that's the first free file descriptor table entry in the table. So that returns 3. And then from the file, it reads hello, and then writes that string to the file descriptor pointed by file descriptor number 1. And here, file descriptor number 1 is already designated as a stand.output, which is the screen. So it writes the hello to the screen. After writing the hello to the stand.output, which is screen, the read does not return any value. It returns 0, and write returns 0. There is a very important concept in the modern Unix file system. Every file that has been opened has an offset. Each time offset is updated every time it is read or written. And the amount of update corresponds to the amount of read or write. The offset value is updated. So if you perform sequential write, then if you read this much, then offset proceeds. And then if you perform read again, then offset is updated this much again. Then like this. So if you look at the details of read system core, file descriptor, buffer, and size. Similarly, for the write, it has file descriptor, buffer, and size. The very, very interesting phenomenon in this function is it does not specify where you are going to read the data from or where you are going to write the data to. So in these two important and essential functions, read and write, it does not contain any clue about where it needs to perform write and read. So in modern operating system memorize the position within a file where the incoming read and write is applied. That is concept of offset. So here in modern operating system, in modern file system, the read and write operation is stateful. Stateful means that operating system maintains a state about read and write operation. Okay, so however, at some time, maybe you want to write different portions of the file other than just sequentially reading a file. For example, when you might want to move forward, skip like next 500 bytes and read the next position, or you may go back 200 bytes and read the file again. For that purpose, we provide the function called lseek. This is seek, and first parameter is file descriptor, and the second parameter is offset, and this is third parameter is option. So you then third parameter specifies how you perform seek. For example, if you there are three options: seek underbar set, and it means that update the offset to the given byte. Seek cur means update the offset with relative to the current location. So there is current offset, and then update offset. Accumulate the offset with respect to the current offset. Third option is seek underbar and it is the size of the file plus offset bytes. So if there is end of the file, and then you want to move the file off and start doing something here, of course that's gonna be right. Okay, so these are offset is very important concept in the modern file system. Again, it memorizes the position where we need to apply read and write operation. And remember, due to the existence of offset, modern file system operation is stateful, meaning that the file system maintains a state of read and write operation. Then is there a file system interface that is not stateful? Of course, yes. So for network file system like NFS, in this file system, the read system core includes the offset as a parameter to the function. So it maintains parameter. In that case, if the file system interface supplies an offset as a parameter, then file system does not have to maintain the state of the read and write. In that case, the file system is stateless. Okay, let's move on to the next page. We will explain the two important abstractions. First one is file object, and second one is open file table. When a file is opened for the first time, the operating system allocates a file object. An important attribute maintained by the file object is the offset. And operating system maintains a set of open file object. In XV6, that is the sample operating system used by our textbook, we maintain it as a table. So we call it as open file table. The advantage and disadvantage of open file table is advantage of maintaining a set of open file object as a table is it is easy to access. But the problem is that because a table is fixed size array, the number of open files that can be opened at the same time in the system is limited by n file. Okay, so there are two important abstractions. First one is open file object, and then the second one is open file table. So when a file is open, then it allocates open file table, open file. Let's say when a file is opened for the first time, then it finds free slots in the open file table and allocate open file object. And then in the file descriptor table, this is file descriptor table. Descriptor table, it allocates a single entry and that maintains a pointer to it. And this is open file table. This is open file table. This is file descriptor table. Okay. There is a system core. It opens a file and it reads a descriptor, 100 bytes. And it performs read of 100 bytes 4 times, 100, 100, 100, 100. For each read, the file is updated, the offset is updated from 0 to 100. On the second read, the offset is updated from 100 to 200. The third read, the file is updated from 2 to 300. However, on the fourth read, because there is no contents left, it does not read anything, returning 0, and file offset remains the same. File object is allocated each time a file is opened. So if the same file called file is opened twice, then 2 file object is allocated and 2 file descriptor is allocated for each file object. Let's say this is object return code is 3 and 4. This is file descriptor number for the first open, and this is the second open. If you perform file descriptor 100 bytes read, then file offset pointer, a file offset for the first file descriptor is updated by 100 from 0 to 100. If you perform read again for the second file descriptor, then the file offset for the second file descriptor is updated from 0 to 100 again, but the file offset for the first file descriptor remains the same. And let me provide an example for LSEC. We open a file, the file offset is set to 0. And then if you perform 200 bytes LSEC, then file offset pointer is updated to 200. And then if you read 550 bytes read, then file descriptor offset is updated from 200 to 250. When you create a child process through the fork system core, the child process inherits the file descriptor from the parent. So all the file descriptor of the child will point to the same file object as the parent file descriptor pointer to. Each object in the open file table maintains a reference count. Reference count is a number of pointer that points to itself, because there can be a number of file descriptor table entry that points to a certain file object. When you close a file, you cannot immediately deallocate the open file table object, because there can be another entry that points to itself. That's the reason why we maintain the reference count for open file object. There is an interesting function called DUP. DUP gets a file system descriptor as its parameter, and as its parameter, the DUP returns another file descriptor. It gets the parameter as a file descriptor and it returns another file descriptor. So DUP system call, if you call DUP with a certain file descriptor, the free spots, and then copies the contents of the file descriptor from here to here. So as a result of calling DUP, they will point to the same file object. The next function is fsync. Write system call, write data to the buffer, and later it saves it to the storage. So there is time interval during which the data stays only at the buffer, and the data is subject to loss when the system crashes. However, some applications require more than eventual guarantees, for example, DBMS. Operating system provides a system call called fsync. If it gets the file descriptor as its parameter. If it returns, then the contents of the dirty blocks associated with the given file descriptor is flushed to the disk. So following is an example of fsync. So we open a file, write something, and then call fsync. And then fsync guarantees that 30 pages for a given file is safely flushed to the disk. There's one thing you might want to remember. If the file is created for the first time, and then when you write something to the file, not only the file blocks are updated, but also the parent directory are updated. So if you want to make the results durable, you also have to make the parent directory durable. So the above code requires fsync to the directory also. There is a function called rename. It is a rename a file to a different name. Very important concept. It is atomic. Okay, so rename function call has to go through a number of steps to finish its operation. However, if the rename fails in the middle of execution, then no interim result will be visible outside. That's what we call by atomic. Let's consider MV foo bar means we change the name of the foo to the bar. Let us provide an example of how we save an updated file in the editor. Let's consider we are using Emacs, for example. And this is a screen, and this is contents, the screen. And somehow you updated this part, and then you write the save command. Then how the editor will save the current contents. This is how it works. It first open a temporary file, and then it saves the current file to this newly created file. Okay, so then new versions of the file is created on the separate file. And then you safely store it to the disk by calling fsync. And then you call a close function to close a file. After closing the file, you perform rename. So you rename the temporary file to the file that has been originally edited. So this is how you save the file. And then as a result of doing this, you ensure that 30 pages are safely stored to the disk. One thing you don't want to forget is that you cannot directly perform fsync to the foo.txt. There is a stat data structure, which contains the details information about a file, like when it has been updated, when it has been modified, when it has been changed. This is time-related information, and also there are lots of information about the permission and the file size and associated inode number. So if you call a function stat, you can access all those files. So let's say you call echo hello, so write hello to the file, name the file, and then get the file, get the status of the file. Then that will show the file name, then number of blocks belong to the file, and then inode number and stuff like that. Okay, this is how stat works. And how we removing the file. Okay, I guess you're all familiar with the command rm. This is remove. This is Linux command line command to remove a file. But if you look at the details of the rm using strace, and then it calls nlink. So rm calls onlink system call. For directory, there is a function called mkdir. It's a function for making a directory, creating a directory. When a directory is first created, it is empty with 2 entries. So it's a parent directory. It's current directory and parent directory. So if you look at this system call trace mkdir foo, then it calls a system call mkdir under the name foo with the permission 0777. And then once it's created, then you perform ls, then there are 2 files, current directory inode and parent directory. You can also have to read. You also have to read the directory. Directory is a file. Directory is a file, but it has a specific structure. Earlier in this class, we've shown that directory is a set of file name and inode number pair. Okay, and this inode number pair can be maintained as a directory entry, array of directory entry, or linked list. There are many ways to organize this pair, linked list, or you can organize those pair of values as a search tree, like B plus tree. So when reading a directory, we use a specific system call other than just read. Read is the read system call for reading a plain file, but we cannot apply that function to reading a directory. So this is sample code. So that's the reason why we define the additional system call read dir. And read dir reads each entry. Read dir reads one entry from directory. So the following is a sample code to read directory entries. This is main function, and we open the current directory, hence assign it to the DP. Okay, and then within the while loop, we read each directory in the directory pointer, and then save to the D, and D is a pointer to the directory entry. And then, so this is kind of, for each directory entry, we print out the inode number and the name. So this while loop scans the pair of a file name and inodes in all its directory entry and prints it to the screen. And after done, it closes the directory. So this is the structure of directory entry. It first contains maximum array of 256 character. It contains inode number, and then it's offset to the next directory entry. And then length of record, and then file type. Okay, so it contains big array, and this is 256 byte. This is name, and there is 4 byte inode number. Then this is offset to the next directory entry, and then record length and type of file. So the type of file means what kind of entry this is for. This is a regular file or symbolic link, something like that. Okay, in deleting a directory, we use rmdir system calls. This remove directory system call actually removes the directory only when it is empty. So if the directory is not empty, then rmdir call fails. There is notion of hard link and soft link. Consider the link system call file 2, and it is something like create new file 2 is created. So if you perform the link ls -i file, this option shows that we need show to see the inode number. So if you perform file 1 and file 2, then both of them will point to the same inode. So the meaning of hard link is there is a directory. Let's say this is dot, and there is file, and it points to some inode number. Okay. If you perform ln file and file 2, and then new file is created under the name file 2, and it'll point to the same inode number. That is what we call hard link. So even though they have the same inode number, it is different, 2 different files under the human name. Okay, this is how we create hard link. First, create an inode and create a link and put it in the directory. So this is why when we remove a file, we call unlink. So there is a directory. And this guy points to an inode. And if this guy points to also inode, let's say this is inode 17, okay? And then these 2 directory entries points to the same inode. So unlink system call removes this link. However, because there is remaining link to the inode number 17, the inode number 17 is going to be deleted when there is no remaining link. Also, the inode has also maintaining the reference counter. So what does unlink do? It checks the reference count within the inode number and remove the link and decrease the reference count. When it reaches 0, it deletes the file. So deleting a file means to free the inode and free the related data blocks. So this is the result of unlink. Let's look at the details of it. So we create the file. It contains HELLO. And then we create a hard link called file F2. Okay. So under the inode number that ends with 84, we have 2 links. Okay. So inode that ends with number 84 has two nodes. Then we create another hard link. Then the inode with that ends with 84 is going to have the link number 3. And then if we remove the file, then the link is going to be, number of links is going to be changed from 3 to 2. If you remove the file 2, then the link number is, the reference count is going to decrease to 1. Okay. There is another link called symbolic link or soft link. It is also called soft link. Hard link cannot create for a directory. It cannot be used for a directory. And hard link cannot create a file to the other file system partition. So, however, the file system people has created a new concept of symbolic link. Symbolic link is slightly different from the hard link. Hard link is regular file, but in symbolic link, then if you create symbolic link, you put minus s options, and then you create a new file f2. Then if you see the contents of file 2, it'll look the same, but in reality they are totally different. Let's say this is original file, this is test.c, and that has a pointer to the inode, for example. And then we issue a command ln-s test.c, and we create a soft link or symbolic link my.c. And then what my.c is, this is a separate file, my.c, this is inode. However, in the data block of my.c, it contains a path, and the path represents the source file of the symbolic link. So that points to the directory entry. So this is what the symbolic link is. So a symbolic link is different file type. If you type ls-l, then it shows the hidden file as well as the file type. Symbolic link, the first field is L, denoting that this is symbolic link. And disadvantage of symbolic link is dangling reference. Let's consider the following scenario. We create a file 2 as a symbolic link, and then we remove the first file. And then, because this is a symbolic link, the file 2 is not aware of the file being removed. So if you type cat file 2, then it says that no such file or directory. So that is the dangling reference. So we have covered the basic interfaces for file system: creating a file, reading, writing, and lseek, reading a file, reading a directory, and creating a directory, and fsync, and hard link, and the symbolic link. That's the end of the class. Thank you.